Welcome to lecture number 6 in the course Finite Element Method, Theory and Implementation. Today's topic will be, as you can see here, global function spaces and the definition of our linear system that we actually want to solve in the end. Or as I've denoted it shortly, finally something a computer can handle after we've discussed about weak derivatives and Sobolev spaces and all those mathematical concepts that are quite nice but can't really be handled on a computer. So today we're going to go one step further towards a system that we can actually solve on the computer. And for that, as a start, I want to summarize the goal, what we want to define, what a linear system in this particular case means. Then in the next part, we will be talking about global function spaces. So after we have discussed the local function spaces in the last lecture, we want to go into detail about the global function spaces. Short reminder about transformation and global DOFs and the piecewise polynomial spaces, our actual global function spaces. And then in the end of this lecture, we want to go steps further in deriving that linear system that we actually solve in the end by starting with a basis representation, then discrete test functions, and then in the end that system that is almost ready to be solved on the computer. So where there is only one tiny detail missing, but we will see all that later on today. Let's start by formulating our goal a bit more precise. So what do we want to do in today's lecture? In order to do this, we do a quick recap what we have until now. So after those first two lectures were just introductions, we had the topic grids in lecture 3. So we tried to find a representation of our domain and in particular get the reference map as a functionality. So we have an array points that has dimension np, so number of points times 2, where each row contains the coordinates of all grid points, so x and y coordinates. That's why we have 2 columns here. Then an array cells with natural numbers or integer numbers, where each row combines the indices of those points that form a certain cell. And then this reference map ft, mapping from the reference cell t hat to a certain cell t for all triangles or all cells that we have. And with that additional functionality to be able to compute the Jacobian and the inverse of the Jacobian or its determinant, all those informations that we need for transformation. And if it's not completely clear why you need those Jacobians and the determinants at this point, you may have wondered about this during the assignments, then I just ask for a little bit more patience, because today at the end of the lecture you will see where all of this is put together and why you need those additional quantities that we have computed. In the following lecture, we talked about weak derivatives and Sobolev spaces. So we derived a mathematical framework that gives us the possibility to form derivatives for piecewise differentiable functions. For example, our piecewise polynomial approximations, or in the motivation that we did in that lecture, those domain parameters that we had for the integrated circuit with those individual electricity parameters that we had. From that, we have derived those Sobolev spaces, in particular the Sobolev space H1 of those functions that have a weak gradient, which is still square integrable, and the additional derived Sobolev space H10, which are all those H1 functions that have particular boundary conditions and so on. After that, in lecture number 5, we talked about the weak formulation and the local basis. So we derived a related problem, the so-called weak form, where we have chosen H10 to be the appropriate solution space. There we have seen that going from that initial strong problem with the Laplacian and those pointwise evaluations of all functions. We could weaken those assumptions and not talk about C2 functions anymore, but instead only about functions that have one weak derivative. And in the end of lecture 5, we derived a local basis for P1 on T hat. So we restricted our considerations to the reference cell T hat and derived local basis functions for the space of polynomials of degree 1, so the basis for the space of linear functions on T hat, such that they fulfill a Lagrangian condition with respect to this cell T hat, so such that every single basis function has the value 1 at one single vertex and 0 at the two other vertices. And now, why and how do we define a linear system? Firstly, why do we want to do that? Well, the reason is quite simple. In order to summarize that, you could say computers can't handle mathematical statements. I think I've mentioned this particular fact many times throughout those lectures already, but it's the key where everything comes together. So a computer can't handle, for example, the infinite dimensional space H1. That's something you can't do on a computer. And also, we don't really have a proper way of using those local basis functions until now. So as of now, we have local basis functions defined on the reference cell, but it's not really useful, and you haven't seen how we can actually put them to a good purpose. And how do we want to define a linear system? Well, we start by talking about the global function spaces. So going from those local spaces of linear functions, we want to go to the global space of piecewise linear functions. And then after having done this, we want to replace those the abstract solution UH and the abstract test function VH by something that has to do with the basis functions. And then in the end, we want to derive a matrix and a vector representing our discrete system such that we can, in the end, solve a linear system of equations that gives us an approximation for our problem. So the rough idea of today will be we take this problem that we have here. You've seen this before. This comes from the weak formulation. So the original problem was something like find u in H10 such that this is true for all v in H10. And then the discretization is that you replace this H10 by our space VH, so the space of piecewise polynomial functions. And then you've got your discrete problem. But that discrete problem doesn't help you if you can't really handle VH. So that's what we're doing today. So the rough idea is to start replacing UH and VH by something that has to do with the basis of this space. And then from that, derive a matrix and a vector such that you end up having a linear system like this. Now let's get to the next part on the agenda, probably the part that you have been curious about before. So those global function spaces. So how can we put this abstract concept of piecewise polynomial spaces to a practical meaning? And for that, quick reminder, transformation of the local basis. This is a picture you've seen before in our lecture on grids. So we have the reference cell, so this very simple triangle between 0 and 1, and we have the reference map that for a particular triangle with vertices A0, 1 and 2 maps all points in T hat to that cell T. And then if you look at this definition, you could write down this reference map easily using the vertex coordinates of A1 and A2. And Additionally, we have also seen that it is simple to compute this inverse of the reference map, or in particular the inverse Jacobian, because we are dealing with a 2 by 2 matrix here, so you can use the determinant, and this should be the adjoint matrix here. Yeah, I think this is a typo here, so that should be the adjoint matrix of AT, and that transposed. Okay, sorry for that. Yeah, so it's quite simple to compute this inverse of the Jacobian. Oh, no, here it's correct. Yeah, and you see that if you have, we have mentioned all of this before, if you have a local basis of some space, for example, pk, although this is of course true for all other types of functions too, but in our particular example, we're talking about basis functions. So if you have a basis of, for example, the space of polynomials on that reference cell, then it's simple to define a basis of that space on an actual grid cell by simply transforming it. So you take the basis function, these ones are basis functions of the polynomial space on T hat, and what you want is basis functions for the space of polynomials on a certain cell T. And then you can define those by simply transforming points. Okay? So if you want to evaluate your basis function on T hat at a certain point, your basis function on T at a certain point, x and y, then you simply take that point x and y, transform it into your reference cell using ft inverse, and evaluate the other basis function there. And because we have constructed ft as an affine linear mapping, everything works out perfectly fine. So if you had a basis function that fulfills a Lagrangian condition with respect to those three vertices, then it will also fulfill a Lagrangian condition, the transformed basis function, with respect to those three, because that's the way we constructed ft. And then we have additionally seen that if you have a gradient and want to compute the gradient of one of those basis functions on T that is also defined by transformation, then you can definitely do that in the same way. The only thing that comes additionally is this inverse Jacobian here, which is a result from the from the chain rule when doing this transformation. So if you want to compute the gradient of a function that is defined by transformation, so the gradient of phi hat of ft inverse, then you have to apply the chain rule here, and this gives you the gradient of the inner function, which is, or the derivative of the inner function, which then is this Jacobian times the gradient of that basis function. Okay? Right, so what we have so far for all cells in our mesh, we can easily define this reference map ft, and with this we can transform those basis functions that we have defined on T hat onto the actual cell T. So if you have, as I've already said, if you have the reference basis and a reference map, it is very simple to construct basis functions on any cell of your grid. And you see here, again, that's important in the further discussion. So we have a very particular notation scheme to be able to get everything clear. So this everything with a hat is on our reference, and in particular this letter phi here represents local basis functions, and then with the hat it's a local basis function on the reference, and this same letter phi with the notation t is a local basis function on a certain cell T. And now, in order to define our global basis functions, we need global degrees of freedom, because it's the same approach that we did in the local case, where we said, all right, well, you have a space and there exist infinitely many ways to define a basis. Hence, we have tried to find a good way to define this basis such that our basis functions are in a certain sense helpful to us, because the coefficients of those basis functions reflected the values at those vertices, and we want to use that same approach. So let's assume we have our reference cell as usual, and we have defined those basis functions with respect to those three vertices of the reference cell, and those were the degrees of freedom for the P1, so for the basis of the linear functions. And then you take your grid, and to define your global degrees of freedom, you want to keep it as close as possible. And if before, in the local case, you have used the three vertices, then now in the global case, you simply use all vertices that you have. So you use as global degrees of freedom all points of your grid. And that's a direct transfer of what has been done in the local case. Because if we use this direct transfer, it is later on much easier to identify which local degree of freedom corresponds with which global degree of freedom. Okay? So again here, just like with the basis functions before in the local case, we have degrees of freedom and they have a certain number. In this case, it's exactly the number, just like the number of points in our grid. And they directly reflect the geometry of the local basis functions. And that's true even if we go to a more complex case. If you were to think about P2, for example, I haven't drawn an example for that, but in the P2 case, for the quadratic functions, we have seen in the last lecture that you use the vertices and the centers of the edges as local degrees of freedom. And you would do that exact same thing also in the global case. So you would again use all points of the grid, so the vertices, and all centers of edges. So that again, it would be easy to identify local and global degrees of freedom. That's very important. And now let's get to that, that crucial part of defining those piecewise polynomial spaces. So we want to consider this space VH that consists of all functions defined on the whole domain, of course, such that if you restrict the function to a single cell, then that function is supposed to be, in this case, a linear function, but in general, a polynomial. So you have a function that is globally defined, and it is not globally a polynomial. That's important. But on each individual cell, it is a linear polynomial. The dimension, that was easier, I think, in the local case, because in the local case you could easily verify the dimension of that space P1, for example. It can be proven, but we're not doing this here, the dimension of this space VH. If you're talking about a particular grid, that's important, right? Those spaces VH, that's why they have the index H, they are always in correspondence with the one particular grid. And if I have one particular grid with a certain number of points, then this space of piecewise linear functions on that grid has the dimension just in the same number as the number of points. Okay? So in order to find out the dimension of the space of piecewise linear functions, you can always just count the points. That's helpful. Maybe in order to imagine this a little easier, why it makes sense, if you think of this whole thing if it were as if it were a framework, so different beams connected in moving linkages here, then it kind of makes sense that you can move every one of those linkages, and in every one of them those beams could change the direction a little, but the flexibility of the whole structure is limited by the number of those linking points that you have here. Okay, so that's the dimension. And then we want to set up a basis. We want to, just like in the local case, find a basis for our space. And in this case, we are denoting those basis functions with the other writing for the Greek letter phi. So instead of using this particular phi, which we have used with an hat for the local basis functions on the reference, and with a superscript t for the local basis on a certain cell t, we now use this writing here, and those are global basis functions. Okay, while these ones here are defined on a single cell, and they are actual polynomials. These ones here, the phi 0 in the other writing, and those basis functions, they are piecewise polynomial functions. Okay? And because the dimension of VH is exactly NP, we can number them from 0 up to NP minus 1. And then, because just like before, we have infinitely many ways to construct a basis, we want to use a global Lagrangian condition. And now it makes sense to, instead of the local case where we had a Lagrangian condition with respect to our 3 vertices of the triangle, now we define a Lagrangian condition with respect to all points of the grid. And then that definition is just the same as before. We want every one of those global basis functions here to have the value 1 at a single point of the grid and the value 0 at all other points of the grid. So that's exactly the same thing. But now, of course, if you have a large number of points in your grid, it becomes kind of obvious that we need those piecewise functions, because it is not possible to find a globally linear function that fulfills this condition for 30 points in a grid, for example. Now, how do these functions look? While it was probably pretty simple to imagine the visualization for an actual linear function, it is not really trivial to imagine those piecewise linear functions. And in order to make it a bit easier, I've depicted them in 2 different ways. What you see here is a basis function. It is one of those basis functions with respect to a Lagrangian condition that we've just spoken about. If you look at this function here, then it is linear on each triangle. You can see here that locally on each triangle, this is a plane, right? So that's a linear function. They have this function here has value 1 at this single point and value 0 at all other grid points. And because of that particular shape that this function has, we call it a hat function, because it kind of looks like one of those hats in Harry Potter or something like this. This image here on the right hand side maybe is also intuitively a bit, maybe it makes it a bit clearer how those functions are defined. So this is a contour map. So this here is the outside contour is phi equals 0, and that inner point here, this yellow color, is phi equal 1. And if you were to draw that underlying grid, then those grid cells are formed like this. Okay. Now, if you look at this, if you look at this image again, you see here that in that middle point you have the value 1. And then what you also see is that these are actually linear functions because those lines are parallel, so it's linearly going down to the surrounding vertices. Now, the next interesting part, you can already see from that hat picture here that this function is 0 in most of the domain, which is, kind of obvious from that picture. So on the other hand, the support of that function is very small. And that's something all global finite element functions have in common. They are always constructed in a way such that they have a very small support, because we will later on see that if we construct them this way, just like the finite difference matrix, we will in the end get a matrix which is very sparse. So most of this linear system is actually 0. So let's look at this, the support of this function phi corresponding with this particular point here in the middle, so this point P15. Well, it has the value 1, as you can see on the picture on the left hand side. It has value 1 here, and it's going down linearly to all surrounding vertices, and it has to be 0 at all other vertices of the grid. In particular, this means that the support of this function is only those cells that are surrounding the vertex. Because if you consider some other cell, for example this one here, in the top right corner, for example, but you could also choose another one, then the Lagrangian condition tells you that the basis function corresponding with point 15 has values 0 at all 3 vertices of this cell. So here, all 3 have in common that phi 15 is equal 0. But now, if a linear function is 0 at 3 points, then it's also 0 everywhere in between. So phi 15 is the constant 0 here, and that same thing is true for all other cells, except those few surrounding the point. Now let's zoom in to this support. So I've drawn this extraction of the grid on the left hand side here, and you see that your point 15 is in the middle, and you see in green color those 6 cells and their indices that are surrounding P15. What's also visible here in the top right corner, you have this cells array. That is the data structure that we introduced when talking about grids, and that stores the indices of the points that connect to a certain cell. Now, what lines can we see here in this cells part of the cells array? You see a line containing the indices 15, 14 and 9. So it's 15, 14 and 9. So this particular line here is corresponding with triangle 15. And then that next line is 9, 10 and 15. So that's T16. And then the last one that you see here is T17 with the vertices 16, 15 and 10. Why is that important right now? The reason why it's important is quite simple, because we want to define those global basis functions by restricting them on each cell and identifying them on each cell with a particular local basis function. Because if I restrict that global function phi 15, if that is restricted to, for example, T16, then it is actually a linear function, because that's what piecewise means. If I restrict it to a certain cell, then it's a linear function on T16. And in particular, that linear function has value 1 at this point here, because that's the way those global basis functions are supposed to be defined. And it has value 0 at those two vertices here. That's again the global Lagrangian condition. Now, if I have a linear function that is 1 at a single vertex and 0 at those two other vertices, that's precisely one of our local basis functions. And which one would it be? Well, it is the local basis function corresponding with this point. Because that local basis function corresponding with the green point in the middle is constructed such that it is linear, value 1 at this green vertex and value 0 at the other vertices. So you can say phi 15 restricted to T16 is exactly the same as one of those local basis functions on T16. And which one is it? Well, if you look at the numbering of those vertices, then you have numbered them locally, starting from the one opposing the longest edge. And we have used that same numbering also for the local basis functions. So this here is vertex 1, this is vertex 2, and this here is vertex 3. So locally, it's the basis function number 3. Oh no, I have to, of course, take my regular numbering scheme, which starts at 0. Sorry. So it should be 0, 1, and 2. And then this is locally basis function number 2. And what's interesting here, you can already observe, if you look at my cells array again and focus at this particular line that corresponds with T16, then you see that my number 15, so the point I'm talking about right now, is in column index number 2, because the column index in the cells array represents precisely the numbering of those local vertices. So this index number 2 can be found by looking at the column index of your 15 in that cells array. Now a bit more about that same thing. If you look at T15, so this triangle here, and look at the numbering scheme, then you start with a point opposing the longest edge, which is precisely our P15. So that has the index 0, represented by the fact that 15 is in column 0. On T16, that's what we discussed before, we have the index 2, which is why 15 is here. And then on T17, this is point or vertex 0, and this here is vertex 1, which is why the 15 is in here. And then you can do that same thing, of course, also for the other 3 surrounding vertex cells. And with this, you're almost done with the construction of your local basis function, because you can simply write it down piecewisely. And that's exactly the core concept of piecewise definitions. I never write a closed analytic formula. I just say, well, if I'm on that triangle, then I have that local function. If I'm on the other triangle, I have the other local function. So I'm simply summarizing what I've analyzed before. On my global basis function, which fulfills a global Lagrangian condition, on each individual cell is either the constant 0 or one local basis function fulfilling a local Lagrangian condition. So phi 15, if I want to identify it on all surrounding cells, well, if I'm in T15, then it is my index 0. If I'm on T16, then my index is 0, 1, 2. If I'm on T17, my index is 0, 1, and so on. And of course, in order to get a global piecewise definition, this 0 else case is also important. So in order to define our global basis functions, the only thing we need is an identification of global versus local indices. And that's why we introduce the so-called DOF map, so a mapping between degrees of freedom. And what is it doing? It's mapping between, on the first hand side, we have the set of indices between 0 and np minus 1, so all point indices or global basis function indices. And we have cells, right? Because that makes sense. If we want to identify global basis function number 15 piecewisely, then we always have to specify if we are in T16 or in T25 and so on. And this DOF map, in the end, gives us this index down here. So it tells you if I'm looking for global basis function 15 and I'm on triangle T16, then my local basis index is 2. Or, as a default case, we usually write that the DOF map returns -1, because we might also have the case that, for example, we ask, well, what is phi 15 on the cell T27, that one here? Well, P15 is not a vertex of T27, so we have no corresponding local basis function. Instead, phi 15 is simply the constant 0. But if someone were to apply this D with index 15 for the global degree of freedom and 27 for the triangle, then we would go into this default case. So we have a global index. Those arrows are pointing a bit weirdly. This was looking a bit differently before. Okay, we have a global index of the degrees of freedom. We have a cell index, and we have, as a result, the local index. So some few examples here. D of 15 and 16 is 2. Why? Well, because if I'm considering global basis function 15 and restrict my considerations to triangle 16, then my corresponding local basis is number 2. And if I insert 15 and 26, then I'm still talking about global basis function 15, but I'm on T26 and 0 is my local index. Okay? So that's a quite elegant concept, because having defined local basis functions on all cells, which we have because we have defined them easily with this transformation approach and the reference map, having defined those local basis functions, it's actually, with this concept of the DOF map, quite simple to define the global basis functions, because we simply do a index, like assignment. So we say that index corresponds to this index on a certain cell. And this is kind of the beauty of finite elements, because the only basis function we actually defined were those simple basis functions on the reference cell. So those we did actually define and derive that they fulfill Lagrangian condition and so on. Then we preserved this during transformation with ft in order to define local basis functions on all cells. And then we use the DOF map to put them together and piecewisely define the global basis functions. And now the next part on our agenda is to actually define our linear system. So going back to what we initially discussed, we want to do something that we can actually solve on the computer. And we have gotten one step, a huge step closer to that by defining those global basis functions, but we still have a few steps to go. And for that, I want to remind you for a second of our problem setting. So this is our discrete weak formulation. So we have a variational problem where we want to check the correctness of this condition for all test functions vh in a certain space and find a function uh in that same space of piecewise polynomial functions, right? So you can, if you read something like this, you can always in your mind think about piecewise linear functions. And we want to find a piecewise linear function such that this is true for all vh that are also piecewise linear. Now let's see what problems we have here. The first problem, how do we find a function in some abstract function space? I mean, of course, it has gotten simpler because vh is the space of piecewise polynomial functions. That's easier than h10, but still asking your computer a question like find uh in some space, that's not doable. And the second problem, we have this condition and we want it to be true for all vh in that space. And the condition like find something such that it's true for all of those infinitely many functions that we have, that's difficult. Because even though vh, the space of piecewise linear functions, is finite dimensional, we still have infinitely many functions in there. So to get a problem out of this that the computer actually can handle, we have to address those two problems here. And we want to do that in the following minutes. And then in the end, we will put it all together. So let's start. The problem is we want to find uh in a certain space vh. And that's kind of problematic. There's infinitely many functions in there. How do we find the right one? And the key word for that is basis representation. We have seen that before when we derived those local basis functions. Every element of the space can be written as a linear combination of the basis functions, and that's exactly what we're going to do now. So assume that you have a basis of that space vh. And those functions are numbered from 0 to np-1, right? np was the number of global degrees of freedom. So our head functions. So for all points in the grid, you have, for each one of them, you have a head function that is 1 there and 0 at the other points. You have that basis. And then you represent some arbitrary function, which is supposed to later be our solution. We represent it using the basis as a linear combination. So that you, in the end, don't have to store some arbitrary function, but in the end, all you need are those coefficients uj, and then you have j from 0 to np-1. So those uj's, if you have a uniquely defined basis, which we have because we have that local, the global Lagrangian condition and so on, and then you can represent every function using that linear combination with those coefficients. And then you can use the linearity of the gradient and the integral. So what do we mean by that? Well, on the left-hand side here, you have an integral over the gradient of your basis, your solution function UH times some b. And where that actually comes from is, well, in the weak formulation, you have integral over gradient of u times gradient of v, right? So that would be our b, but I've done it here in the more general form because what I'm doing now would be true even if we're not talking about gradients of basis functions, but some arbitrary b. So what can we do? Well, we do at first plug in that thing we did up here. So this is the gradient of a sum from j equals 0 to np minus 1, uj, phi j. And that whole thing times b. And then, as I've written down in that point, we use the linearity of the gradient. What does linearity mean in this case? It means that you can take summations and scalar multiplication and exchange it with the operator that is the gradient. So meaning that we can take that gradient into our summation. So we have a sum of still from j equals 0 to np minus 1. And then, well, uj is just the coefficient, so just a scalar multiplication. So we leave that as it is, and then have a gradient of phi j. Because that thing is linear, that gradient, okay? So you have reduced the gradient of your function UH, or the problem of finding a gradient of your function UH, to gradients of basis functions. That's already a good step. And then we can go one step further and use the fact that the integral is also linear, so we can take summations and scalar multiplications also out of the integral, and we arrive at a sum over all j equals 0 to np minus 1, uj, scalar multiplication, times the integral over omega of gradient of phi j times b. So I've done this basis representation approach, and then I've seen that integrating something that has to do with the basis can be reduced to actually integrating those basis functions and then afterwards multiplying with the coefficients and summing up over all degrees of freedom. That is kind of intuitively clear, but it's still nice to know. Okay, so our equation, which we call star here because we need it later on, is given that the integral over gradient of UH times B is equal to the sum over coefficients times an integral with the basis functions. And why is that cool? Well, that's cool because if you have one particular space VH and a fixed basis of that space VH and some function B, then you can compute those, and that's something that's constant, all the time the same. And if you want to find your UH, that problem now becomes find all those coefficients UJ. Okay? So instead of finding one of those infinitely many functions in your space VH, you actually only have to find the right NP coefficients. Okay? So instead of finding some abstract function, we only want to find NP real numbers, our solution coefficients. And also side remark here, because we have constructed those basis functions such that they fulfill a global Lagrangian condition, our coefficients here, those UJs, are just like in the local case, again representing the function values at those particular points. meaning that UH at a particular point, P, let's say PM, is precisely UM, so that coefficient with that same index. Now, that next problem we have denoted is that the condition is supposed to be true for all VH in VH. And yeah, in contrast to the other one, which we could simply derive, I've chosen that this problem is sufficiently interesting to make a quick lemma out of it. So this concept that we have to check for a condition for all that has to be true for all functions in a certain space, that is something that might occur again. And I think it's in general interesting to have this result. So assume that you have a certain space and you want to, and you have a basis of that space, so just our setting, and you want to check a certain condition. Then my lemma says, if my equality, this one here, is true for all basis functions, then it's already also true for all functions in the space. Okay, so you see here, if this holds for all phi I, then it actually holds for all VH in the whole space. That would mean that instead of testing with all VH in our space, we could also just test with all basis functions. And that's a huge difference because it's not infinitely many functions anymore. It's just NP many functions. And of course, I can't just tell you a lemma without explaining why it makes sense. So this is one of the few cases throughout this lecture series where I will actually do a proof. So let's see, what do we want to prove? Well, we want to see if this condition here is true if this condition holds. Okay? So let's do, and this proof is not going to be complicated. Let's start on the left side with an integral over omega of b times gradient VH. And this b is again a placeholder, so in the actual practical problem this is going to be gradient UH. But here this result is more general, so that's why I've chosen to just use b as a general function. Okay. Then first step we're doing is we use again a basis representation for VH. Okay, so I say that I can write my VH as a sum over all degrees of freedom of some, or let's denote it with I instead of J, some VI times global basis function phi I. Okay, so that's the same approach as before. And then we can plug this in. And then we have here b times gradient of, and then the sum I equals 0 to np minus 1 vi phi I. Okay, now we can, just like before, use the argument that the gradient is a linear operator, so we can exchange summation and scalar multiplication with the gradient. So we have integral over omega of b times, and then sum for I equals 0 to np minus 1. Sorry for that. Gradient, and then we have the vi and the gradient of phi I. Okay? So we've just taken this gradient operator to the inside of that summation. And then the next step is that the scalar multiplication is also a linear operation, so we can take that multiplication with b inside of our summation. So we can say this is equal to an integral over omega, and we have a sum for I equals 0 to np minus 1, and then vi and b times gradient phi I. And then the last step is we can use the linearity of the integral and take that all in there. So we take the scalar multiplication and the summation out of the integral. So it's sum over I equals 0 to np minus 1 vi, and then an integral over omega of b times gradient phi I. And now that is exactly what's printed up here in this equation. So according to the prerequisites of our lemma, this thing here is now equal to an integral over f times phi I. So I can use now my condition 1, and I leave my summation as it is, I leave vi as it is, and I have an integral over omega, and there f times phi I. Okay? So I've just used the prerequisites of this lemma. And then I can reverse my whole process of using linearity. So the first step is that I take the summation and the scalar multiplication into the integral again. So then we have an integral over omega of sum from I equals 0 to np minus 1, and that's vi times f phi I. And then of course I can also take that f out of this summation, so it's an integral over omega of f times a sum for I equals 0 to np minus 1 vi times phi I. And then here I can see again that this was actually my basis representation of VH. So that precisely is the integral over omega of f times VH. And now we have proven what we wanted to prove. And what did we do in that proof? Well, we have used a basis representation for our element in the space. That's one core ingredient. And the other core ingredient is that all operators that we are dealing with here are linear. So the gradient is linear and the integral is also linear. And that's why we could take all those combinations out, then use our prerequisite, and then put it back together. Now this lemma can also be helpful in the future in other use cases, because it's in general an interesting observation that if you have to check for a certain condition for all functions in or for all elements in space, then it's always sufficient to check that condition for all basis functions, as long as that condition only involves linear contributions. And that's kind of interesting. And what does that mean? Well, instead of testing with all functions VH in our space, we can reformulate the problem and write we want to find UH such that this equality is true for all basis functions phi I. And that's a huge difference, because instead of having to test with infinitely many functions, this is only exactly NP many functions. And now we're going towards that last step of derivation of the linear system. So, starting from this problem, find UH in VH such that the gradient of UH times gradient of some basis function is integrated just like f times that basis function. Okay, that's where we start, and well, the first thing we want to use here, of course, is that other thing that we derived before, and that's the basis representation for UH. And we have introduced this basis representation for UH and derived the fact that we can replace this find UH by find a vector U with NP components such that, and then we have replaced the UH by this basis representation involving a summation over coefficients times basis functions. Firstly, notation. A quick reminder, just like in the finite difference method, this U, which contains coefficients for all degrees of freedom, is called a DOF vector. So a degree of freedom vector, because it has as many coefficients or components as we have degrees of freedom in the system. And that's what later on represents functions. So in all finite element implementations, you use these DOF vectors to represent your functions. Of course, they are with respect to a certain grid and a certain finite element space, but the DOF vector is what represents a function. And what is this now? Well, you see here that we want to find NP coefficients such that this equality is true for all NP test functions. And that already looks quite a lot like a linear system, because we want to find NP variables such that NP equations are true. And in particular, you take this part with the gradients of the two basis functions. And because we have two indices here, the j index coming from our solution, which we will call the ansatz functions, because that's the ansatz you're making in order to find your solution, and the I index coming from the test functions. That's why you use them to define Sij. Important here, there is an index shift. So Sij, with I first and then j second, is defined as the product of phi j times phi I with gradients. Of course, this is not important here, but later on it will be important. So there are other problems where it's not symmetric and you can't just exchange it. Okay, yeah, that's one part. And the other part, it's not difficult to guess, that integral over f times the test function will be put in a vector, so we only have one index here. And we call those two things S and L for a reason. And that reason is that in the original implementation or the original use cases for finite element methods, you were talking about elasticity and mechanics systems. And that left-hand side thing, with those products of the gradients, was reflecting the stiffness of the system. And that right-hand side thing, with the function f, was representing the load that you were putting onto your system. That's why S, your left-hand side system matrix, is called the stiffness matrix, and L, the right-hand side vector, is the load vector. And if you put this all together, then you have a linear system of dimension NP times NP, with the matrix, stiffness matrix S, containing integrals over products of gradients of basis functions, L containing your right-hand side, and U, the DOF vector, with NP components with all coefficients for the basis functions. That's a linear system now. And it seems as if we are done at this point. So Technically, you could say, okay, this now is a linear system. I can compute those components Sij and Li, put this in my computer, solve for u, and be done with it. And that's almost true, but not completely. Because still, on your computer, it would be a tiny bit difficult to tell him that he is supposed to integrate the gradient of a piecewise linear function. Well, how do you do that? And that's why we take a closer look at those two parts. And firstly, a closer look on our right-hand side load vector. So we have an integral over f times phi I. The first thing we can always do when integrating over a domain omega and having a grid that fills the whole domain, we can split this integral over omega into a sum over integrals over the individual cells. So instead of summing over omega, we are summing over all triangles or all cells in TH and integrate over the individual cells. And it's very intuitively clear that if you do this summation, then you again have integrated over the whole domain. Okay, and the rest stays the same for now. And that next step, well, what's the next step? Now, this part here, this integrand, is only on one particular cell T. We've seen earlier today that those piecewise global functions on each individual cell are actually polynomial functions. And more precisely, we can represent phi I on a certain cell T using that DOF map of the cell T and inserting the global index I. So we leave our summation, we leave our integral, we leave our f. But instead of using the global basis function phi I, I'm taking the local basis function of cell T, and the index is the DOF map applied to index I, the global index, and the index of my cell T. Okay, that's the identification of that global basis function phi I with certain local basis function corresponding to that same degree of freedom. And then, one step further, we see that those local basis functions were defined by transformation of reference basis functions. So I'm leaving my summation, leaving the integral, I'm leaving the f, but instead of writing phi t, I'm writing phi hat with that same index, and phi hat of, and what was the transformation thing? We used ft inverse on that point, right? And now I'm writing dx, we'll see later y. So instead of evaluating phi t, I'm evaluating phi hat, but before I can evaluate phi hat, because this is defined on the reference, I'm transforming with the inverse of ft. And now, what I'm doing, the next important step, is integral transformation. Okay, in 1D, it's called substitution, but in multiple dimensions, you call it an integral transformation. And I will, you can look up the integral transformation theorem, you can find it on Wikipedia or something, but I'll write it for a second. So if I have a certain set, let's call it B, and that set is formed as the application, okay, no, I'm not calling it phi here maybe, let's call that function, I don't know what we call it, let's call it gamma, of some other set A, okay, those are two sets. Then I can write down the integral over B of some function f as the integral over a of f of gamma of x, and that whole thing is scaled with the determinant of the Jacobian of gamma. That is the integral transformation formula. So you can switch between two integration domains by A, transforming your input arguments, and B, scaling with the determinant of the Jacobian. So this one here represents an area scaling, so that kind of reflects the ratio between the area of A and the area of B. And yeah, the other thing is just transformation. So in our cases, we can use Ft, so our reference map, as the transformation, and then we see that we are precisely in this setting here, because our T here is the set B, which is formed as the transformation applied to some other set, and then we can go back and transform to our original set. So let's leave the summation here, but we switch to an integral over t hat. Okay? Then you leave your f. Of course, you have to write f of ft of x hat. Here you see why I've started writing the dx now, because I can write dx hat in order to denote again that I'm integrating over t hat now. And then what's important here, what's really interesting, is that if you write down your basis function, that there nothing has changed so far, then I have to, according to my transformation theorem, I have to replace the original argument by the transformation. So that means, until here, it's all the same, but instead of writing x, I have to write ft of x hat, just like here. And here you can finally see why this definition of the reference map made so much sense. Because by defining this reference map from t hat to t, which sounded counterintuitive because we always had to write the inverse, we see here now that by in the end transforming our integrals to t hat, we don't have to deal with inverses at all, because we form ft inverse of ft of x hat. So that cancels out and we're left with x hat. And I can summarize t in tau h. I've forgotten this determinant. I can take the determinant out of the integral because it's constant. So the determinant of d ft. Now you see why this determinant is interesting. It's only interesting because it is the scaling between those two integrals that we are transforming. And then you are left with an integral over t hat of your right-hand side function and your local basis function depending on x hat dx hat. And that, if you think about it, is amazing because we are left with an integral over our simple domain x hat, and what we have to integrate there is our simple local basis function on x hat, on t hat. So we integrate this simple basis function here, which was in the linear case something like x hat or y hat or 1 minus x minus y, and we're integrating this over the simple triangle And that's all we need to do to form our root vector on the right hand side, because we have done transformation twice. We have defined those basis functions on the global grid using the transformation, and then we have transformed the integrals again. And by doing those two transformations, they have in the inner inside cancelled out, and we're left with a formula that is quite simple actually. So, summary, you start by splitting the integrals, then you identify the global and the local basis functions using the DOF map. You use the definition of the local basis function as a transformation of the local reference basis, and then you do an integral transformation, you get the determinant of the Jacobian, and you get rid of this FT inverse and only have an integral over the reference cell of the reference basis. And for that left-hand side part in the stiffness matrix, you are starting off the same way. So you start off by splitting your integrals into integrals over individual grid cells. Then you replace your global basis function using the DOF map, so that global index J becomes DOF map of J and cell T, and global index I becomes DOF map of I and T. So nothing spectacular here. But we're talking about gradients. So if we insert the definition that our local basis function on cell T is actually a transformation of the reference basis, we have to make sure that our gradients are transformed in the right way. And that's done using this chain rule that we have mentioned before. So if I form the derivative of phi hat of ft inverse, that's chain rule. That's just like saying f of g of x prime is g prime of x times f prime of g of x. Right? That's one-dimensional chain rule, and that same thing happens here. So if we form the gradient of this concatenation of functions, we get this additional factor. So this dft inverse here in front of both gradients, that's the scaling. Intuitively, this also becomes quite clear why it's necessary. If you think about one of those basis functions, so let's say I have a basis function defined on my reference cell. So each one of those edges has length 1. And the other basis function is defined on a triangle that looks the same, but my edges are, this one here is the same, but let's say I have 1 over 100 here. And this one is also 1 over 100. Okay, just a factor 100 times smaller. Now imagine that I have the gradient of this function here. I have a basis function there, value 1 at this vertex, value 0 at the other vertices. Then this gradient goes over a distance of 1 down from 1 to 0. So if you look at that triangle from the side, so at that three-dimensional visualization, you would have that one point, that other point, and your function would go down linearly from 1 to 0 over a distance of 1. In that other triangle, because the triangle is so much smaller, you would go down from 0 to 1 over 100, but your function values would again shrink from 1 to 0. So that slope here on that side would be, around 1, because over a distance of 1 I'm going down from 1 to 0. And here, or let's say minus 1, and here my slope, in that other case, my slope would be around minus 100, because I'm going also down from 1 to 0, but over a distance of only 1 by 100. And in order to get to equal out this fact, because, well, if I'm expressing one function as the transformation of another, I have also to make sure that the gradients are the same. That's why you are rescaling the gradients. And yeah, that we have also seen. So if you have a triangle like this, which is very small, then your gradient would balance this out. Because if you have a triangle with those coordinates, then your ft would have a matrix of 1 over 100 and 1 over 100 here, plus something. That dft would be just this matrix, and the inverse of that thing would just be 100 and 100, and that would weigh out the fact that you are replacing a gradient over a small triangle by a gradient over a big triangle. So that factor 100 here balances out the fact that here we only have a factor scaling 1. Okay, but that's just a side effect of how you can explain why we need this inverse Jacobian thing in the chain rule. And then you use that same thing, so you're transforming your integrals and you get rid of ft inverse here, and you get the determinant as an area scaling, and in the end you are left with integrals over gradients of reference basis functions, and those integrals are also over the reference. So put it all together, you have those two formulas, one for the load vector, one for the stiffness matrix, and look at those individual parts. Determinants of Jacobians of reference maps, we have done that in the assignment, I think number 3 or 4 it was lecture number 3. It's easy to compute because the DFT is a 2 by 2 matrix, so that determinant is a determinant of a 2 by 2 matrix. No problem. Next part, evaluation of basis functions and gradients of basis functions at points in the reference. That's also simple, because you have to evaluate your basis functions, for example 1 minus x hat minus y hat, something like that, at points in your reference. So it's evaluating simple functions at simple points. That's good. And the next part, those inverse Jacobians of the reference maps, they are also not so complicated because they are a direct result of the determinants. You can easily compute them. And what's also important is that all those parts have already been implemented. So you have done in assignment number 4 those determinants of the reference map, of the Jacobian of the reference map, and those inverse Jacobians. And in the next assignment you have implemented the evaluation of the basis and the gradients of the basis. So almost all of this is done already. Of course, the summation over triangle cells is also not difficult because each cell is represented as one line in your cells array. The only thing we're missing are those integrals. So what we have not discussed yet is integration over the reference cell. We can already imagine that it's not super difficult because the reference cell is so simple, but we haven't discussed it yet. And that's going to be the last step towards a finished implementation. How can we integrate something over the reference cell? And what we are going to do is we want to discuss numerical integration, so quadrature, on reference cells, in order to approximate our integrals and finally be able to set up our linear system. Okay, thank you for your attention and see you in the next lecture.